So what I want to do today is do just a recap of what we did this semester, and then we'll have a review of some of the material, and I'll do that through PRS questions. And halfway through, well, we don't have a halfway through because Drew is not here. Yeah, so somebody calls time at some point, then we can take a break, and then we'll do a show and tell of all the goodies that I brought today. Okay, so that's the game plan. And so in terms of what we did this semester, I mean, we covered a lot of ground, right? We basically looked at what is inside the box, both the hardware and the software, and the 5 units that we went through: processor design, memory system, parallelism, I/O and file systems, and networking, right? So those are the 5 major topics, and in every one of these things, we sort of saw the connection, symbiotic relationship between hardware and software. When we looked at processor design, we talked about how instruction sets are designed from a compiler perspective in terms of generating efficient code, and so all of that, instruction set design falls out of how do you compile high-level language constructs, right? And then we looked at how to efficiently execute it, efficiently implement the processor both in a simple manner and a pipeline manner, and then what you need to grab the attention of the processor when something untoward happens, whether it is internal problems or external interrupts, right? And then on the software side, we looked at processor as a black box, and then how you schedule that in order to run your program. So that was the first unit, and the second unit, similarly for memory system. On the hardware side, we looked at what is required. First of all, in just sort of understanding why we needed memory management in the first place, and we looked at that aspect of it, and then we said, what is it that we need in hardware to support memory management, and then what are the different, if you have paging, what are the different techniques for doing page replacements and things like that, right? So those are all the issues that we looked at, and then on the hardware side, we said for efficiency, we want to make sure that our memory accesses are fast, and so we designed caches that live both address caches, which is the TLB, and the data caches for instructions and data that sits inside the processor and makes life good in terms of performance. And then on the I/O and file system side, on the hardware side, we already saw what interrupts were and how to deal with them, and then we started looking at high-level interfaces, right? Higher-level hardware interfaces like DMA controllers and disk controllers and so on. And then on the software side, we said, if disk is an important subsystem, then how do you use that storage system in order to build the software system that we all rely on, which is the file system, and so that's the 4th unit, and then the last, well, actually that's the 3rd unit, and the fourth unit is the parallelism, the fact that every box now is a multiprocessor, and therefore what we want to do is understand how to exploit the inherent parallelism. And we all became experts at parallelism already, because when we're designing data path and control sequence, it is you're exploiting all the parallelism that exists inside the data path, and so sort of elevating that to the level of programming, in high-level language. And so thread-based programming is what we looked at on the software side, and what we need in order to support the threads in the operating system. And on the hardware side, we said, well, if multiple threads are going to be accessing shared data, then you have to provide synchronization for that. What is it that we need as primitives in the hardware in order to support synchronization among multiple threads? So those are all the hardware issues that we looked at. And then the last thing that we covered is the networking part of it, although we flipped it in terms of order of coverage because of your project. And there we looked at the evolution of networking hardware, and some of which we'll see later on when we do the show and tell. And we found that the different protocols that exist in terms of media access and control are things that we already saw in the context of just a single processor and memory interaction. And then on the software side, it was very interesting, because now we are talking about losing control right? Things are going out of your box, and therefore you have to worry about what might happen to data that you might send out, and data that come back in, even in the absence of any malicious users, just the fact that networks are unreliable. And so we looked at the protocol stack, what needs to happen in the software in order to make sure that when things go bad, we can recover from that and still be able to do what we needed to do. So that's sort of the big picture of the entire semester in a nutshell. I gave you this at the beginning of the semester, and hopefully now it all comes back together. Are there any questions? So where do we go from here? if you get interested enough that yes, systems is interesting and exciting, I want to do more about that, well, there are lots of things that you can do. So that's the reason that we have this course so early on in the curriculum at the sophomore level. It's a 2000 level course, and of course some of you may be taking it later in your tenure at Georgia Tech, but the intent is that you can take it in the sophomore year so that you have a couple of years to dive deeper into systems if you're interested in it. So and the things that we looked at is the architecture side, the operating system side, and the networking side. And so you can take those three threads and move forward if you're interested in that. And so there are a couple of threads that that are there that build on this basis. One is, I think it's called internetworking, information and networking. So that is one thread, and the other one is a platform thread, right? So both of these build on top of this, that you can dive deeper into systems topics. And specifically in the junior year, there are three courses that at the 3000 level, there are three courses that follow on to this. One is, if you're interested in the hardware aspect of it and you want to go and build a real processor, because you did do build a real processor, but you never got around to actually implementing it in terms of chips and testing it and so on. And that experience you can get if you take 3110. Okay, 3110 is the course that's a hardware design course where you start with Xilinx board and you design the instruction set, implement it, test it, and see your creation working, right? That's always a happy thing to do. Just like all the way from Hello World program to building a processor, every one of those things is an experience, and you enjoy it when it actually works. So that's one course that's a follow-on to that. The second course is 3210, which is the operating systems course. And the operating systems course, the intent is in 2200, what we learned all the basic concepts, right? And we implemented pieces of the operating system in the different projects, like a scheduler or a memory manager or a network protocol stack. So those were all isolated pieces that you implemented, but you haven't built the whole thing, right? And let me tell you, even if you go to a company like Microsoft or Apple and so on and so forth, where they're building operating systems, you're not going to start building operating systems from scratch. They're always going to take an existing one and then sort of build on top of it, right? And so in that sense, the 3210 course, what it does is, well, you understood the concepts. Now let's look at a production operating system, how it looks, and what are the, when we talked about memory management in 2200, I introduced towards the end of it the idea of multi-level page tables, right? So initially we talked about just page table as one level of indirection, but we quickly saw that if you really wanted to have space for the page table in memory, it's just impossible, right? Because given the size of the architecture these days. And therefore, multi-level page tables is a way to combat that problem. And if you look at production operating systems, those are the kinds of things that you'll see as all the difficulty in scaling the algorithms that we learned or the data structures that we learned in 2200 to a production operating system, what things actually happen. And so in 3220, the operating systems course, you will dive more into the details of Linux kernel and implement pieces of algorithms in the production kernel, right? So that you can actually see how non-trivial it is to make changes to a production kernel. And that kind of real world experience is extremely useful. And I heard from some of the students who graduated from 2200 and went on to work, they said, one of the things that we don't get in going through a curriculum like what we have is really looking at production code, right? I mean, you all build pieces of programs, pieces of software, but you don't have an idea what a production code looks like. And so 3220 is an opportunity to look at production code and see how you can make modifications to that and so on and so forth, right? So that is 3220, and 3251 is the networking course, and that builds on the basics that we learned here and dives a lot more deeper into routing protocols and TCP/IP protocol stack, design of that, because we talked about a protocol stack, and we had a very simple idea of what a reliable transport protocol would look like, but in order to actually build it, it's a huge state machine. We looked at state machines in the context of a processor, right? And TCP/IP protocol is also a state machine. It's a huge state machine, and so you have to worry about how you do the connection establishment, connection management in the steady state, and then connection teardown. All those things are things that you learn in 3251. So those are the courses at the junior level. Then at the senior level, there are courses like 4210, which is where you learn more advanced concepts in operating systems. And we scratched the surface in terms of distributed systems in this course, right? So I just mentioned the fact that you have networking, and then on top of that you can build software, but we never talked a lot about how you build distributed systems. So a lot of those kinds of concepts get covered in 4210. That is the advanced operating systems course. I don't think 4210 is a pick in any of the threads that I know of, but it is a specialization that you can take if you're interested in it. And a lot of students who want to specialize in systems, especially if they're looking at potentially going to grad school, they take that course. Okay, so that is 4210. And similarly, there are courses in the architecture track, 4290, which is the advanced high performance computer architecture. So a lot of the things that we learned here will new concepts you'll learn in that course. And similarly, networking, I don't remember the number off the top of my head. There's a 4000 level course, which is a networking course that also gives you more advanced concepts in networking. Do you know? 4251, thank you. 4251 is the course that gives you more advanced concepts. So just to summarize, so from 2200, you can go on to CS 3210. This is the OS, or you can go to CS 3110. This is the architecture, and you can go on to CS 3251, which is the networking, and then you can go on to CS 4210. And in fact, in the case of in the case of architecture, you don't even need this course. You can directly, if you don't want to do hardware hacking, you can, because this is, at this course, in this course, there are not a whole lot of new concepts you're going to learn. It is more exposure to production quality stuff that you won't get an experience with. So there are not going to be a lot of new concepts that you learn in these things. And whereas here you will get more new concepts. This is a high performance computer architecture. Okay, and then similarly over here you have CS 4251. Okay, and I'll just call it advanced networking. I don't know what it is. Okay. Pardon me? Networking 2? Okay. Yeah, okay. Okay. So that's the sequence that, yeah. Which one? Yeah. 32. Oh, sorry. Yeah, okay. Thank you. Yeah. 32. Yeah, that's good. So that's the and you can if you wanted to take this course without taking this course, it is possible. You just have to request the professor whether you can do that. In fact, you may have to look at the prerequisite structure. I have a feeling that you don't need this course as a prerequisite. If you had 2200, then you can go directly to 4210. This is advanced OS. Okay. Any questions? Okay. Now I'm going to switch to PRS mode. So if you have your PRS units, you can fire that up. Okay, the first PRS we're going to do, okay, it's kind of a fun survey. And for this, some of these questions, if you want your identity to be anonymous, you can switch your PRS units with your neighbor. I mean, so we won't, I won't grade this. So you don't have to worry about this being graded. So you can actually switch your PRS units with your neighbors if you want anonymity for some of these questions that I'm going to ask you. Okay, everybody ready? Oh, the channel. Did I start it? I haven't really started it, have I? D is the channel, and I want to do a new session. Well, you think concepts though. Think concepts. Yeah, you don't be narrowly focused on homework or projects. What was intellectually challenging and appealing to you? Okay. And we may have failed in the delivery or whatever, but but the question is really to do with the intellectual appeal. All right. Well, look at this. There's a huge spike at number 5. Number 5 is networking. Okay. Huge spike at 5. That's interesting. Is that because you saw it towards the end? All right, so let's go to the next one. Same set of choices. The question is different. Let's see. Oh, here it is, all over the place. And let's see. The highest bar is for 4. Caches. You don't like caches? And then memory management, and then processor design. Interesting. Okay, so what was 2? Processor scheduling is okay. I/O is okay. No, not I/O. Oh, networking is okay. I/O is okay. Interesting. By the way, this survey should inspire you to go and complete the opinion survey if you haven't done that. How many of you plan to do the opinion survey? How many of you have done it already? Oh, that's good. So how many of you plan to do it? Pardon me? Okay. Uh, so do it while you remember. Okay, so the question was devote more class time. Yeah, this is sort of obviously expected because you like networking the most, and devote more time to networking. Okay, that's a good point. So here's where you can stoke my ego. Uh, or brutally maim my ego. Well, at least nobody said they hated it. Uh, it was okay, it was good. Nobody said it confused me. So I'm happy that, 4 and 5 nobody chose. Although somebody chose 6, I don't know what that is. You can say how much you expect to read. All right. So um, yeah. So it seems like quite a few have said uh, I like this. Quite a few have said that they are reading a significant portion of the book. That was good. And you should read the book if you want to do well in the exam. No opinion. Let's see. So some have chosen memory systems related. Uh, okay, the biggest spike that I see is in the memory systems related topics. That's interesting because I thought the memory systems is the one that is got a lot of coverage in the book. So basically, okay, I get it. I'll think about this. So hopefully nobody is going to choose number 9. Don't pick number 9. That'll bruise my ego completely. All right. So let's see. Maximum was for 5. It said I had no opinion before I took the course. wow, you oh, right. Okay, so a few for number 8, and number 1, love systems already love it even more. So I was looking for somebody who said I hated it and now I love it. Number 7, let's see. Oh, there's one. Would you believe it? There's one person who said I hated systems before and now I love it. That's good. Okay, so this is very interesting. But you have the majority of the class is total apathy towards towards the course, which is disturbing. Maybe it is just the end of the semester, and you guys are tired. I can understand that. So here is the real proof of the pudding. Alright, so there's 3 people leaving planet Earth. Number 3, oh, this is good. So I'll take another course in networking. So that's good. And few have said take another course in architecture and operating systems. And 4, there's one guy who says I'll never take another course in systems. Okay. At least I haven't made anybody switch majors yet. That's good. All right. Nice. Attended pretty regularly. Okay, so that's pretty good. Um, okay. All right. So, uh, 2 people thought it was a complete waste of time, but most of you thought it was useful. That's good. Most of you thought it was useful. That's good to see. Be nice to them. All right. Okay, that's good. Most of you thought they did a good job. That's good. Well, there's always choice number 8 and 9. Oh, so this, yeah, 5, I don't know how 5 is, should have been, that's a mistake. It's okay. All right, so you guys are generous. That's nice. All right, so that's it. Now we're going to switch to a PRS of course material. So if you had your PRS unit switched, so maybe what I should do is I should close this, right? Is there a way to, maybe I should close this and restart it. I want to end this session, yes. Pardon me? Yeah, yeah. Okay, so let's do, you may have seen some of these questions if you attended the recitation, because I gave the TAs these questions to use in the recitation. But I thought it would be useful to do it here also again. Hey, don't do this to me. Need more time? All right, so this is good. You guys are getting ready for the exam, I can tell. Okay, once again, a few of you have, you said it's a bad idea, but for the wrong reason. So it's really the fact that it's, they're different functionalities, so number 4 is the right answer. All right. So most of you have the right answer, so excellent. This is just a warm up. Wait till you get towards the end of these questions. Wow, this is good. So some of you picked number 3, saying that it's a point-to-point network. It is not. You know, these days it's becoming more physically like that, but still logically Ethernet is a bus. Okay, and so if you chose number 3, then here's a chance for you to clarify if you have doubts about Ethernet. Any doubts about Ethernet? Okay, it's you know, pardon me? Point to point meaning that you directly communicate with somebody else, so you have a dedicated link, right? That's a point to point network. Which logically, so logically it's a bus, and if you have a point to point network, then you'll never have collisions, right? You'll never have to wait for anybody because you have a dedicated link, right? And but these days, Ethernet is becoming like that in terms of physical realization, because you have a dedicated link from you to a switch, and so you never have collisions. You don't experience any collisions. But logically, it's still the protocol is the CSMA CD protocol, which is implementing, making it appear like a bus. Shane? Pardon me? No, if it is point to point and it is full duplex, right? If it is point to point, it is full duplex, then there is no collision. If it is point to point but it is half duplex, then you are right. Only one can do at a time. Okay? Just to see if you are all awake. All right, so that's good. So most of you have the right answer. Some of you have picked 4. Hub is not the same as a switch. We've talked about this in the class, right? Hub is just electrically equivalent to a bus. So all the devices can connect to it, and internally it is giving you the same CSMA CD protocol. Switch, on the other hand, is allowing you the freedom that you never experience any collision, because when you send a packet, internally the switch is going to buffer it, right? So that's the difference. And so the hub is not a switch. It's really Ethernet in a box. Okay. So now you start doing a little bit of not yet, but well, so the answer here you guys are saying, many of you have chosen could be meant for any node on the internet. If you look at the packet format here, what we are doing here is if the packet format is just the IP address and the message, then it could be meant for any node on the internet. But when you stick a MAC address in front of it, what you're saying is you're sending it to a particular node which is available on the local area network, right? MAC address is not something that is visible on the internet, right? So MAC address is only visible within a local area network. So the minute you tack on a MAC address, then it is being sent to some other node on the same local area network, and yes, it could be meaningful in Ethernet or a token ring, but really, if you look at the rest of the packet format, there is an IP address. If it is just meant for another node on the local area network in an Ethernet or a token ring, then you'll have just the MAC address and the message. But when you have a MAC address and then an IP address and then a message, then you obviously want this IP address to be interpreted by somebody, right? Whoever is whose MAC address matches this is going to interpret this IP address. Now who is the guy that can do that? The router. That's the only node that knows about IP addresses, right? And so the right answer is number 4 here. It's meant for a special node in the LAN that is connected to the internet. Everybody with me here? I mean, so you've got to just do a process of elimination. You can see that cannot be meant for any node in the internet, because if you have a MAC address, why are you putting that MAC address in a packet? And it could be for an Ethernet, but then there is an IP address. And if this has to be interpreted, any node on the Ethernet cannot interpret it. So it has to be a special node that can do it. Everybody with me here? Any questions on that? Okay, that's good. So if you got the difference between hub and switch from the previous question, then you'll know the answer to this question. If you don't answer this question correctly, then I know that you still haven't gotten the distinction between the hub and the switch. Okay, so most of you have the right answer. That's good. So, when, as I said, when you're connecting a node to a switch, then you're not going to have a collision. So it's not a single collision domain. And it's not exactly 2 collision domains either, because every node, if it can connect to the switch, then each of those is an independent collision domain. So it is going to be as many collision domains as the number of ports that you have on the switch. If I have an 8-port switch, and if I connect 8 devices to it, each of those devices are in a collision domain unto themselves. So in other words, there are as many collision domains as the number of ports that you have available on that switch. Everybody with me here on this? Anyone confused about collision domain? I mean, you can feel free to ask questions. Here's the chance, right? Sort of a review. So if you have doubts, this is a chance to clarify it. Don't be shy. All semester you have not been shy. Don't be shy for the last class. Fine, Okay, so most of you have the right answer. So you know that the average latency for transmission is not going to be it's not going to be always less than the Ethernet, because it really depends on the load. So it is really under load, high load, that it results in better throughput compared to the Ethernet. So the right answer is 3. So if you have any questions on that, now is the chance to ask. Okay, many of you chose number 4, and that would be true only under high load, not always, because if there is no load, then Ethernet is much faster, right? Because there's no collision, you can send your packets very quickly. Whereas on the token ring, you have to wait for your token before you can start transmitting, right? And so Ethernet is more optimistic, and token ring is pessimistic, right? And pessimistic protocols generally tend to be having higher latency, right? And that's the reason that you will find that if the load is very light, then you will end up having higher average latency in token ring as compared to Ethernet. So the right answer is 3 here. Okay, now you start doing some math, mental math maybe. I expect a perfect answer. Wow. See, packet size is 1500 bytes, which means that's the total size of the packet. So if you take off you cannot add the header to the packet, right? The message is part of the packet. So don't confuse packet size with the message size, right? Packet size is a transport parameter. Message size is the application parameter, right? So you create a message at the application level, give it to the transport, and the transport tacks on a header to it and then creates a packet, right? And therefore, if the packet size is 1500, then and payload is synonymous with the message, right? Payload is synonymous with message. So the payload is the difference between the packet size and the header size. So the right answer is 2. Okay? And most of you have the right answer. That's good. Want some more time or? Okay, so it's a pretty simple problem, right? So most of you have the right answer. Basically, message size is 100,000 bytes, and packet size, and you know that packet size is 1100 and the header size is 100. So the payload in every packet can be 1,000 bytes. So if the message size is 100,000 bytes, then you need 100 packets to send it. So the right answer is 1. Okay, any questions on Shashank? Depends on in Ethernet it's about 1100 something or the other. I don't remember exactly the number. That's the Ethernet packet size is 1100 something, and then you take off some for the header if it's an IP header and MAC address and so on. Okay. The same question, but now you have packet loss. Okay, so most of you the right answer. Some of you have 5, close but not exactly right. So you know that when you send 100 packets, you lose 10 packets. So it's 10% packet loss. Then you send 10 packets, 10% packet loss, you're going to lose 1 packet, right? So you have to send the last packet. And for the last packet, you don't worry about fractional loss, so you end up with 111. Everybody with me here? Okay. So the right answer is 4 here. Okay, so now this that's the last PRS question. So this question that I'm going to do, I'm going to sort of work it out for you. Just give you the sort of idea behind that, because it's a more involved question. It's a worked out example in your book, and I can assure you that I won't give you a question of this magnitude in the final exam, but parts of this question will help you to sort of understand what is going on. So in this question we are saying message size is 1900 kilobits, and header size is 1000, and packet size is 20 kbits. So if you add these two, you get 20 kbits, right? So 20 kbits is the sum of these two things, and the bandwidth on the wire is 400,000 bits per second. Time of flight is 2 seconds. window size is 10, sender overhead, receiver overhead, negligible, size of ACK is negligible. Okay, so you know what is the end-to-end time for latency for message transmission? Remember that? What is the end-to-end latency? So you've got the I don't know what I call it, but let's call it T. There is there is the wire delay, right? Wire delay is how quickly you can place bits on the wire, right? And in front of that, there is a sender overhead. So this is the time that you take for software overhead, protocol processing that needs to happen in software, right? Then once you're done with that, the wire delay for placing the bits on the wire. Okay, then what is the next component? Time of flight is the third component. That is the time it takes for the message to travel from source to destination. And then the receiver overhead. So these are the components of the latency, right? And so I'm going to give you a sketch of this solution, but I'm not going to talk in detail. But what you're given are things like the bandwidth on the wire. The bandwidth on the wire, where will it be useful in this equation? Pardon me? Time on the wire, TW, right? That's the one that is going to be affected by the bandwidth on the wire. Pardon me? No, S is sender overhead, R is receiver overhead. That's a software overhead, and we made it 0 here, right? Pardon me? Okay. So S is the sender overhead. That's the protocol processing, software overhead, and R is the receiver overhead. That is the protocol processing on the receiving side. And TW comes from this bandwidth on the wire, and time of flight 2 seconds. That's this term here, right? Is that idea clear? So these are the things that constitute the time for sending a packet on the wire. Okay, and now suppose you say 10% packet loss, then you can actually compute the number of data packets transmitted. So here we're not talking about the number of the time for this, but we're just asking how many data packets are transmitted, because we're saying ACK messages are negligible, so we don't worry about ACK messages getting lost or time for it or anything like that. And so the only thing we're worried about is the data packets. So you can do something similar to what we did in the previous problem, right? So for just computing the data loss or the packet loss, do we need this? Do we need these two terms? The bandwidth on the wire and the time of flight? You don't need that, right? So it is only talking about loss of packets, and that is entirely coming from the loss rate, and given the message size and the packet size, how many packets you're going to start with in order to send on the wire, and how many may get lost, right? Everybody with me here? Okay, that's similar to what we did earlier. So the interesting question is, if you assume that the network is error-free, what is the total time to accomplish this whole message transmission? Because a single message, this is the time it's going to take, right? But we know that in network protocol, we are pipelining the messages, right? So it is not like we're sending one packet and then waiting to send another packet and so on, but you're going to pipeline it. And how many packets will you pipeline? That is coming from the window size, right? The window size says that send 10 packets, then you wait. How long do you wait? How long do you wait, Michael? What are you waiting for? Acknowledgement, right? So waiting for an acknowledgement. So if I send a packet, when is the earliest you'll get an acknowledgement? It'll so the time of flight is 2 seconds. So it'll be 4 seconds into from the time of transmission that I'll see the acknowledgement coming back, right? And but it is actually how much time it took for me to place the packet on the wire, right? after that is when I compute, right? So in order to know how much, so after it reaches, after I place the packet on the wire, 4 seconds later I'll get the acknowledgement, right? Is that point clear? Right? After 4 seconds I'll get acknowledgement. And so if you look at the timeline for this, it'll look like this. If you look at the timeline, what we're doing is you're placing 10 packets, and then for placing every packet it takes 0.05 seconds. How do I get that? Well, if you do the math on this, the sender overhead plus the packet time plus the time of flight plus the receiver overhead, that gives you the time it'll take for the packet to reach the destination, right? Think about the very first packet. The amount of time it's going to take is the packet size divided by the bandwidth. That gives you the time on the wire. Okay, that is this term, and then the time of flight is 2 seconds, right? And so this is the time it will take for the for the packet to actually get to the destination, right? So it is 2.05 seconds. So if you do the simplification of this, it is 2.05 seconds later that the destination will get that packet, and then it is immediately going to send an ACK back because there's no packet loss, no corruption, no nothing, right? So it's going to immediately send the packet back, and it takes 0 time to send the ACK packet, okay? But to place the packet on the wire, but it's going to take 2 seconds because of time of flight for that the acknowledgement to reach the source. And so after 4.05 seconds, you're going to see the first ACK. Is that idea clear? Right? So the first ACK is going to come back after, this is the amount of time it takes to place the packet on the wire, and from the end of this to the ACK coming back, it's going to take 4 seconds. So that's when I can start sending the next packet, because I send a window of 10 packets and wait, and the amount of time I wait is for the ACK to come back, and that will be 4.05 seconds. Everybody with me here? Alazar? That's the ACK packet you're saying, right? So that's where you said the sender overhead is 0, receiver overhead is 0, and ACK packet generation is 0, right? So as soon as the receiver gets the packet, you can place the ACK packet on the wire without losing any time. Okay, so the only thing that you're paying for is the ACK packet to traverse the time of flight to reach the source. Maba? First acknowledgement, right? And how quickly will I get the subsequent acknowledgements? Because 0.05 seconds I'm going to send a new packet, right? And so there's a train of packets that went, and each of those packets were separated by 0.05 seconds. Similarly, the train of ACK packets that are coming back are going to be separated by 0.05 seconds. 4.05 seconds is all that the sender has to wait before it starts retransmitting again, right? Because as soon as 4.05 seconds have expired, I've seen the first ACK packet, I can send the next packet because my window is 10, right? So now I have only 9 outstanding, so I can start sending the next one. And it takes 0.05 seconds to send that. The next ACK is going to come within that time, and so on. Well, if there's only 10 packets that if I want to send, then it is going to take 4.05 plus the 9 acknowledgement packets to come back, right? And that is, 4.5, right? So that's the amount of time it will take. But now we've got a message is much bigger than that, right? So the message is actually, what was the size of the message? It was 200,000. The message was 1900 k bits, and so you have to break it up into so the number of data packets that you need is 100 data packets that you need, right? And in every cycle, I send 10 packets and wait for an acknowledgement, and so I can do this as soon as the first acknowledgement comes back. I can send the next train of 10 packets. As soon as the first acknowledgement for that train of 10 packets come back, I can send the next packet, next train of 10 packets. So in other words, I need a cycle, in one cycle of 4.05 seconds, I've sent successfully 10 packets. Okay, the next 4.05 seconds, I'll send the next 10 packets. Everybody with me here? Scott?
There was like a corruption to occur as the last
Yeah.
chain of 10 packets.
Yeah.
The last one could have been met.
Yeah.
But you're already sending the next chain of 10.
Yeah. No, you wouldn't send the last one, because the 10th one, because you did not get an ACK, right? So you would be, so here we are assuming error-free transmission. It makes it much more complicated if you want to introduce errors, right? So let's just focus on the error-free transmission. With error-free transmission, I can send 10 packets, and 4.05 seconds later, I get the acknowledgement. Then I start sending the next packet, and because they're going to come in a train of acknowledgements, I can send the next 10 packets in succession, right? So in every 4.05 seconds, I've successfully sent 10 packets. Everybody with me here? And I have to repeat this 10 times, because 100 packets need to be sent, right? So that's what we're going to do is, in one 4.05 seconds, you can send 10 packets and wait for the ACK for the packets. And so to send 100 packets, we need 10 such duty cycles, right? And so the total time to send all the 100 packets is 40.5 seconds, 10 times this, right? Now, this goes back to what Maba was saying in the beginning. At the end of this, all the 100 packets are gone. How many ACKs have I received? I've received only one ACK for the last 10 packets. The remaining 9 ACKs have to come back, right? And the remaining 9 ACKs will take 0.05 seconds each. So that's the additional time that you have to wait. And so the total time to accomplish the message delivery is the sum of these two. Okay, and this picture shows you the sort of the timeline of how things happen in the sender. Yeah, Shane. 0.05 is coming from this equation right here. Right, the amount of time it takes, this part of it, right, the time to place the packet on the wire. Okay, because it's not zero time to place the packet on the wire. It depends on the size of the packet and the bandwidth you have to the network, right? So that's where this one comes from. Okay, Maba? Yeah. So the message size is 1900 k bits, and the packet size is 20 k bits, right? So in other words, in every message, I can have 1900 bits. So you need, 100 packets to be sent. Okay. Okay. Everybody with me here on this one? Can I give you this problem on the exam? Some parts of it you might see. But this gives you the big picture of when I have multiple packets to be sent, how it all works out. So let's stop here, and I want to do the show and tell. And unless you want, I'm going to set up things. So if you want to take a quick break and come back, or if you just want to hang around and start looking at it, it's fine too. Lots of fun toys I have here.